Hey there, and welcome. Ever stop to think about your morning coffee, or even the air you're breathing right now? Our entire world is basically built on mixtures. So what's really going on when you stir sugar into your drink and it just disappears? Well, today we're going to unpack the incredible chemistry of solutions.
So here's what we've got on tap. First, we'll cover the absolute basics. What even is a solution? Then, we'll look at its limits, what controls it, the laws that rule it, and finally, we'll get into some of its super cool and useful properties.
All right, let's dive right in. First things first, before we get into all the nitty-gritty details, we have to agree on what a solution actually is. So let's start with the most fundamental building blocks.
Okay, the one word you absolutely have to remember here is homogeneous. What does that mean? It just means the mixture is perfectly, totally uniform. Once it's mixed, you can't see the separate bits and pieces anymore. Think about salt in water. Once you stir it in, you can't see the little salt crystals anymore, right? The whole thing is now salt water, exactly the same at the top, the bottom, and everywhere in between.
So every solution has two main players on the team. You've got the solvent, that's the big guy, the one present in the largest amount doing all the dissolving. And then you have the solute, that's the stuff that gets dissolved and there's less of it. So back to our saltwater example. Water is the solvent, and the salt, that's the solute. See? Simple as that.
Now, this is where it gets really cool, because this totally shatters a common idea people have. We usually think of solutions as just, a solid dissolving in a liquid, like our seawater example. But check this out. You can have a solid dissolved in another solid, like a metal alloy, like brass. You can have a gas dissolved in a liquid. Hello, carbonated water. And you can even have a gas dissolved in another gas. In fact, the air we're breathing right now is a perfect example. It's just a solution of oxygen, nitrogen, and a bunch of other gases.
Okay, so you're mixing stuff together, but can you just keep going forever? Can you just keep dumping solutes into a solvent without end? Is there a limit? Well, that brings us to a really important idea: saturation. Basically, when is a solution officially full?
All right, picture this. You're making a glass of iced tea. You add a spoonful of sugar, stir it, and poof, it's gone. You add another. Still good. But as you keep adding more and more, you notice it's taking longer to disappear. Until finally, no matter how much you stir, there's just a pile of sugar sitting at the bottom of the glass. Boom. You've just hit saturation. The tea is holding every last bit of sugar it possibly can under those conditions.
But what if you could cheat? What if you could trick the solution into holding even more solute than it's supposed to? Well, that's what we call a supersaturated solution. It is seriously cool, but it's also super unstable. The way you do it is usually by heating up a solution, dissolving a ton of solute in it while it's hot, and then letting it cool down very, very carefully. Now it's holding way more than it should, and it's just waiting for an excuse to fall apart. A single tap, or even a tiny grain of dust, can trigger this incredible reaction where all that extra solute instantly crystallizes right in front of you. It's amazing.
Okay, so we know some things mix and some things, well, they just don't. Oil and water, right? But why? What's controlling this whole process? Let's dig into the key factors that are really pulling the strings here.
It pretty much boils down to three big things. First, you've got the nature of the solute and the solvent themselves, what they're made of. Second is temperature. And third, and this one is a really big deal for gases, is pressure.
And this brings us to the #1 golden rule of solubility. You've probably heard it: like dissolves like. It's all about something called molecular polarity. So, polar solvents, like good old water, are amazing at dissolving other polar things, like salt. But on the other hand, you have nonpolar solvents, like benzene, and they're what you need to dissolve nonpolar stuff, like naphthalene, which is what they use in mothballs. This is exactly why oil and water don't mix. It's simple. Oil is nonpolar, water is polar. They're just not like each other.
Now, when it comes to temperature, things get a little tricky. It's not a simple heat is always better situation. For most solids, sure, like potassium chloride here, you crank up the heat, you give the molecules more energy, and they dissolve way better. We call that an endothermic process. But, and this is a big but, for some compounds, like sodium sulfate, the dissolving process actually releases heat. It gets warmer. In these cases, which we call exothermic, increasing the temperature actually makes them less soluble. I know, it sounds totally backward, but it's one of those weird and wonderful rules of chemistry.
All right, so we've got the factors. Now let's see how they get baked into actual scientific laws. These are the rules of the game that let us predict and even calculate exactly how a solution is going to behave.
First up, we have Henry's law.
This one is all about getting gases to dissolve in liquids. And you know what? It's beautifully simple. It's a direct relationship. The more pressure you put on a gas above a liquid, the more of that gas will dissolve into the liquid. That's it.
And you already know this law, even if you don't know its name. Think about a can of soda. While it's sealed, it's under high pressure, right? That's what forces all that carbon dioxide gas to stay dissolved in the liquid. But the second you crack it open, that psst sound, you release the pressure. All of a sudden, the CO2 is way less soluble, and it comes rushing out as bubbles. So, in the simplest terms, more pressure means more fizz.
But hey, in science, there are always a few rebels, right? Gases like ammonia and CO2 are interesting exceptions. They are way, way more soluble in water than Henry's law says they should be. And the reason is, they're not just dissolving, they're actually chemically reacting with the water. That reaction pulls even more of the gas into the solution, breaking the normal rule.
Okay, next up is Raoult's law. This one's all about something called vapor pressure. Fancy term, but it just means how easily a liquid wants to escape and become a gas. In a perfect world, this is super predictable. But we don't live in a perfect world. Sometimes when you mix two liquids, the molecules are less attracted to each other than they were before. They can escape more easily, which gives you a higher vapor pressure. We call that a positive deviation. And if they're more attracted to each other, they're held in tight, they can't escape as easily, and you get a lower vapor pressure. And that's, you guessed it, a negative deviation.
All right, for our last section, we're going to get into something really fascinating. We're talking about a special set of properties that only show up when you make a solution. And what's so weird about them is that they don't care what you dissolve. They only care how much of it you dissolve.
These are called colligative properties. And the big idea, the main takeaway, is that they only depend on the number of solute particles you've added, the concentration, not what those particles actually are. So when you add any solute that doesn't evaporate easily, a few things always happen. The vapor pressure goes down, the boiling point goes up, the freezing point goes down, and you create something called osmotic pressure.
And this freezing point depression is something you've seen a million times for sure. Why do we put salt on icy roads in the winter? We're not just melting the ice, we're creating a saltwater solution, and that solution has a lower freezing point than regular water. So the ice melts even when it's still below freezing outside. It's the exact same science behind putting antifreeze in your car's radiator to keep it from freezing up.
So there you have it. Solutions are everywhere, explaining so much of the world around us. From the air we breathe to the oceans, it's all chemistry. The next time you stir your coffee or see those salt trucks out in the winter, you'll know exactly what's going on. It really makes you wonder, right? What other amazing scientific principles are just hiding in plain sight, waiting for us to notice? Thanks for tuning in.